Have you noticed that this summer feels hotter than ever? You're not imagining it. According to the World Meteorological Organization, the year 2024 set a troubling record. The Earth's average temperature rose to 1.6 degrees Celsius above pre-industrial levels. For the first time, the planet surpassed the 1.5 degrees Celsius threshold, not just for a day or a month, but for an entire year. January 2025 pushed the boundary further, with a recorded average rise of 1.75 degrees Celsius. Amid this sweltering data, a surprising contradiction emerges. Some scientists suggest that we are still technically in an ice age, more precisely, a warm interglacial period within one. The Earth, they warn, may be sliding toward another massive freeze, despite the heat waves engulfing our cities. How can these two realities coexist? To answer that, we must look not just at today's weather, but at the deep history of our planet. 1. The climate threshold, 1.5 degrees Celsius, and its consequences crossing the 1.5 degrees Celsius limit may seem minor, but it's a scientifically significant boundary. This threshold is linked to profound shifts in ecological and atmospheric systems. Polar ice melts faster, sea levels rise, and weather extremes intensify. Entire ecosystems from coral reefs to Arctic tundras begin to collapse. And yet, this number doesn't tell the whole story. Earth's climate operates on cycles far beyond human times. The warming we see today is just one phase in a complex, fluctuating system that has swung between hothouse climates and frozen hellscapes over millions of years. 2. Still in an ice age. By geological standards, we are living in an Isogete Quaternary ice age, which began about 2.6 million years ago. What sets it apart is the presence of permanent ice sheets at the poles. During this period, the Earth has alternated between glacial periods, extensive ice coverage, and interglacial's warmer phases. We are currently about 11,700 years into an interglacial known as the Holocene. So even while cities bake under record temperatures, massive ice sheets still cling to Antarctica and Greenland. The presence of these polar ice masses is the technical marker of an ice age. 3. The clockwork of the heavens. Orbital drivers of climate. Serbian mathematician Milutin Milankovic, in the early 20th century, proposed a revolutionary theory. The cycles of ice and warmth are driven largely by variations in Earth's orbit and axial tilt. These are now known as the Milankovitch cycles, and they unfold over tens of thousands of years. Eccentricity. This refers to the shape of Earth's orbit around the Sun. It shifts from nearly circular to more elliptical in a 100,000-year cycle. Greater eccentricity means more variation in solar energy received during different times of the year. B. Axial tilt. Obliquity. Earth's axis tilts between about 22.1 and 24.5 in a 41,000-year cycle. A greater tilt increases seasonal extremes, which can cause more summer melting in polar regions and more snowfall in winter. C. Precession. Like a spinning top, Earth's rotational axis wobbles over a 25,800-year cycle. This alters the timing of the seasons in relation to Earth's position in its orbit. Together, these factors influence how much solar energy reaches different parts of the Earth during different seasons. When less energy reaches the northern hemisphere in summer, snow and ice can persist and grow, eventually triggering glaciation. 4. The last great freeze and the warning it holds. The last glacial period peaked around 20,000 years ago. Vast ice sheets covered much of North America, Europe, and Asia. Sea levels dropped by more than 100 meters, exposing vast continental shelves. The world was colder, drier, and dramatically different. Then came a relatively abrupt shift. Global temperatures warmed, glaciers retreated, and human civilizations began to flourish. Agriculture arose during this warm interglacial, and modern history unfolded under relatively stable climatic conditions. But stability is deceptive. Earth's climate history is anything but steady. 5. Are we due for another ice age? The last interglacial, before the Holocene, known as the Eocene, lasted about 10,000 to 15,000 years. We're already within that same window. Does this mean we are on the verge of another glacial advance? Some models suggest that under natural conditions, Earth might already be cooling. However, anthropogenic greenhouse gas emissions have likely delayed the onset of the next glacial period by tens of thousands of years. Still, If the balance shifts through abrupt oceanic or atmospheric changes, or disruptions to ocean currents, like the Gulf Stream, descent into a colder world could begin sooner than expected. 6. The Gulf Stream, a climate tipping point. The Gulf Stream is part of the Atlantic Meridional Overturning Circulation (AMOC), a vast conveyor belt of ocean currents that redistributes heat around the planet. Warm water from the tropics flows northward, cools, and sinks in the North Atlantic, dragging surface currents behind it. If this system weakens or stops due to fresh meltwater from Greenland, for example, heat transfer slows. This could plunge Europe and parts of North America into a deep freeze. Even as global temperatures rise, models suggest that just a 1% increase in freshwater input per year could halt the Gulf Stream in a century. Without this warm water pump, climate chaos could ensue. Regional cooling, shifts in monsoon patterns, and disruptions to marine ecosystems. 7. Ice in the forecast. While today's headlines are dominated by heatwaves, wildfires, and floods, the possibility of future glaciation remains. The mechanisms that drive ice ages haven't disappeared. They're simply being masked, for now, by human-induced warming. What will happen when our fossil-fueled intervention ends? Will Earth rebound with a vengeance? Could we trigger feedback loops that inadvertently accelerate the arrival of the next ice age? These are not questions for science fiction. They are urgent inquiries for climatologists, policymakers, and anyone concerned about humanity's long-term survival. If you were to look beyond the urban landscape, beneath the soil, beyond the oceans and the high mountain glaciers, you would find an archive, one built not with paper and ink, but with ice, rock, and sediment. This archive tells the story of Earth's many glacial and interglacial cycles. It holds clues about abrupt freezes, catastrophic melts, and slow, rhythmic climate swings that have shaped life itself. To understand where we might be going, we need to understand where we've been. The evidence is astonishing and ancient. 1. The geological proof of ice. Ages. The concept of ice ages wasn't accepted until the 19th century. In 1837, Swiss geologist Louis Agassiz proposed that large portions of Europe had once been covered in thick glaciers. His peers laughed at him, but slowly, the evidence accumulated. Striations and erratic strokes, dragged by glaciers, leave behind deep grooves in bedrock. These striations point in the direction of glacier movement. Even more compelling are glacial erratics, massive boulders carried far from their source by ice and deposited alone on flat plains. Their very presence, in unexpected locations, told a clear story of past glacial action. B. Moraines and drumlins. Moraines are ridges formed by accumulated glacial debris. Drumlins are elongated hills shaped beneath moving ice. Both are remnants of glaciers' advance and retreat, revealing the extent and motion of ancient ice sheets. 2. Ice cores, frozen time capsules in Antarctica and Greenland. Scientists have drilled deep into the ice, extracting cylindrical cores that extend hundreds of thousands of years into the past. These cores contain layers of snowfall compacted over millennia, bubbles of ancient air, sealed in the ice, isotope ratios, like oxygen 18 versus oxygen 16, that reveal past temperatures. One of the most powerful findings from ice cores is that Earth's climate has not been stable. Instead, it has oscillated with regularity, and sometimes with astonishing speed. 3. The snowball. Earth hypothesis. Go back far enough, around 700 million years, and you reach one of the most extreme theories in Earth science: snowball Earth. During this time, it's believed that glaciers reached the equator, and the oceans were largely covered in ice. The causes: the positioning of continents near the equator, increasing rock weathering and CO drawdown, a weakened greenhouse effect, possibly even a trigger, like a massive volcanic eruption or asteroid strike. Eventually, volcanic CO built up, warming the planet enough to melt the ice. This extreme freeze-thaw cycle may have catalyzed the rise of complex life, as it created intense environmental pressures that encouraged biological innovation. 4. Ice ages in the Quaternary period. The Quaternary period, beginning 2.6 million years ago, has seen at least 50 cycles of glacial and interglacial phases. The most well-known glacial periods include Gunz, Mindel, Riss, and Wadrem, named after rivers in Europe. The last glacial maximum approximately 20,000 years ago, when ice sheets were at their peak extent. Climate signatures during glacial periods. sea levels dropped over 100 meters *, vast regions became tundra or permafrost rainforest, and temperate forest belts contracted drastically. Human populations survived. In refugia, isolated habitable zones, these cycles are recorded not just in ice, but in marine sediment, stalagmites, lake beds, and tree rings. Point 5. Human survival in the ice. Our ancestors didn't just survive the ice age, they adapted and thrived. Cave paintings in Lascaux, France and Altamira, Spain depict animals like woolly mammoths, woolly rhinos, and reindeer. These weren't fantasy, they were daily encounters. Tools and firestone tools, fire pits, bone needles, and fur clothing show how early Homo sapiens evolved survival strategies even against the bitter cold. Migration and genetics. Periods of glaciation shaped human migration. Genetic evidence suggests repeated bottlenecks and expansions as populations were squeezed into ice-free zones and later expanded when climates warmed. 6. The Little Ice Age, a modern chill from roughly 1300 to 1850 CE. Earth experienced a glacial phase known as the Little Ice Age. Key events: the freezing of the Thames River in London. Crops failing across Europe. Famine and disease, including the Black Death. Thriving under climate stress. Vikings abandoning Greenland as temperatures dropped. The causes remain debated. Some possibilities: a period of low solar activity, the Maunder minimum, high volcanic activity producing reflective aerosols, changes in oceanic circulation. This relatively recent cold period reveals how even modest shifts in global temperature, 1–2 degrees Celsius, can have massive societal consequences. 7. Life under ice. Biology's resilience. Life has endured multiple glaciations, not just survived, but diversified. Refugia ecosystems. Macronton, in warm springs, ocean vents, or belts served as biological refuges. Here, plants, animals, and microbes persisted and evolved. B. Ice Age giants. The Pleistocene was home to megafauna, mammoths, saber-toothed cats, glyptodons, and cave bears. Many of these species went extinct during the post-glacial warming, a mystery still debated over hunting versus climate change. Point 8. The rhythms of ice and fire. Earth's climate pulses in response to orbital mechanics, Milankovitch cycles, plate tectonics, shifting ocean currents, volcanic eruptions, altering atmospheric chemistry. Feedback loops, especially involving ice and albedo reflectivity. We now understand that even small triggers can tip a system already balanced on a knife's edge. These lessons from deep time should caution us as we approach new human-driven climate thresholds. From the snowball Earth to the Little Ice Age, the planet's past is filled with cold warnings. Our current warming period is abnormal in its speed and scale, but it's occurring atop a much older, slower-moving cycle of planetary cooling. Understanding these cycles isn't just academic. It helps us predict the resilience of ecosystems, the reliability of agriculture, and even the habitability of continents. In short, our future depends on the deep knowledge of Earth's past. Future tipping points. When will the next ice age begin? 1. Standing at a crossroads. Earth today is in a peculiar phase. We are living in what geologists call an interglacial period, a warm break in the middle of a longer ice age. But this interglacial, the Holocene, has been unusually stable for over 11,000 years, allowing human civilization to bloom. Yet beneath this apparent stability lies a climate system sensitive to the smallest nudges, one that has shifted dramatically before and may shift again. The question is not if another ice age will arrive, but when. And more urgently, are we delaying it or hastening it? 2. Milankovitch cycles, the cosmic metronome. In the early 20th century, Serbian scientist Milutin Milankovitch proposed that periodic changes in Earth's orbit and tilt govern the timing of ice ages. There are 3 major Milankovitch cycles. A. Eccentricity 100,000-year cycle. Earth's orbit shifts between more circular and more elliptical shapes. This affects the distance from the Sun during different times of the year. B. Obliquity 41,000-year cycle. Earth's axial tilt varies from approximately 22.1 to approximately 24.5. More tilt equals more extreme seasons. Less tilt equals milder seasons. C. Precession 26,000-year cycle. Earth wobbles like a spinning top, shifting the timing of seasons relative to the orbit. These cycles influence how much sunlight insolation reaches the high latitudes during summer. Less summer sun means less melting of winter snow, a recipe for glaciation. When all three cycles align in a way that reduces northern hemisphere summer insolation, an ice age can begin. Right now, we're in a combination that should start a gradual cooling. But there's a problem. 3. The greenhouse effect. A human override. Human activity, especially since the Industrial Revolution, has pumped vast quantities of carbon dioxide, CO, and methane into the atmosphere. These greenhouse gases trap heat, acting like a thermal blanket around the planet. Current CO levels have now exceeded 420 parts per million, far above the 280 ppm of the pre-industrial era and likely higher than any level in the past 3 million years. That this warming is overriding the natural Milankovitch-driven cooling. Models suggest that if CO remains high, it could delay the next ice age by 50,000 to 100,000 years. In effect, we've hit the pause button on Earth's glacial heartbeat. 4. But could climate change cause a sudden freeze? Ironically, global warming may paradoxically trigger abrupt regional cooling or even accelerate ice sheet growth under the wrong conditions. Here's how. A disruption of ocean currents, the Atlantic meridional overturning circulation, AMOC, which includes the Gulf Stream, carries warm tropical waters northward. This system keeps Western Europe mild, but melting Greenland ice is pouring fresh water into the North Atlantic, making it less salty and less dense. If enough fresh water accumulates, the circulation could weaken or shut down. This could plunge Europe and parts of North America into a sudden cold snap, while the tropics get even hotter. In past ice ages, this kind of shutdown was a key player in triggering or intensifying glaciation. B. More snowfall equals more ice. A warmer atmosphere holds more moisture. In high latitudes, this can mean more snowfall. Paradoxically, that extra snow can start accumulating into new ice sheets, especially if summer's cool. 5. Other potential triggers besides orbital mechanics and greenhouse gases. Earth's climate responds to other major forces. A. Volcanic activity. Massive eruptions like Toba, approximately 74,000 years ago, or Tambora, 1815, can blast sulfur aerosols into the stratosphere, reflecting sunlight and triggering years of cooling. A supervolcano eruption could drop global temperatures enough to kickstart glaciation. B. Asteroid impacts. Like volcanoes, impacts can throw dust and particles into the air, blocking sunlight and cooling the planet for years. These impact winters may have helped cause past mass extinctions. C. Plate tectonics. Over millions of years, continental drift rearranges ocean currents and wind patterns. If large land masses drift toward the poles, ice sheets can more easily form and persist. 6. How likely is a new ice age soon? Given current conditions, scientists mostly agree another ice age is inevitable but not imminent. With greenhouse gas levels so high, glaciation is unlikely in the next several thousand years. If emissions are rapidly curbed, a gradual return to cooling may resume in tens of thousands of years. Asterisk. But if AMOC collapses, Greenland melts, or volcanic cooling occurs, regional cold periods could emerge much sooner, within centuries. 7. How will humanity be affected? A. Agriculture and food farming is finely tuned to current climate zones. A shift toward glaciation would devastate arable land in the northern hemisphere. B. Sea level drop. In full glaciation, sea levels could drop over 100 meters, exposing new land but altering coastlines and ecosystems. C. Mass migration. As cold zones expand southward, millions could be forced to relocate, reversing the modern trend of population growth in northern latitudes. D. Geopolitical tension. Access to resources like fresh water, fertile land, and stable climates could spark new conflicts. 8. Can we predict the next ice age? Predicting the timing of future glaciation is notoriously hard due to incomplete data about Earth's internal processes, the chaotic nature of weather and ocean dynamics, *, the unknowns of human emissions, solar cycles, and volcanic activity.